Hello, hi everyone. We're going to cover today how to run Apache Spark on Kubernetes. So it will be myself. I'm Yaron. I'm CTO and founder for Iguazio. And we have with me Marcelo, a longtime big data expert and Spark expert from our team that is going to also show the demo and talk about the details. So with that, let's move to the first slide. So first, let's talk about the challenges today. One of the critical elements when you're building machine learning and AI is to build a production pipeline. So not only work with CSVs, Excel spreadsheets, etc. In research, the real problem is deploying that in production. In production, you have real data, you have streaming data, you have to do ETL from operational databases, you have to integrate with APIs. And once you bring all that data in, you have to run analytics at scale, not only on within a single Jupyter container, image or container or notebook, but you want to scale out the processing of the data. And once you've done that, you run training and serving and all of that pipeline. And Spark is very instrumental in processing data at scale, but on the same time, it needs to coexist with other elements of the stack, as we're going to present. And as part of that, we want to move into a microservices architecture and use Kubernetes as sort of the baseline for that. When we look into the entire pipelines for machine learning and or AI, then we have different steps. We have the step of data ingestion, followed by preparation, which is joining, aggregating, splitting data, and turning it into meaningful features. Followed by training, where in the training you want to run various algorithms, various training models on the same data set to generate this model. Once you've ran the training, you want to move to a validation step, take some portions of the data, run the model against it, and verify that you have decent accuracy. And finally, you want to deploy those models alongside with APIs that come together with them for the feature vectors. If we're looking into this entire pipeline, we can see that Spark can play a major role in some of those steps, especially around data ingestion, processing, data preparation, and analytics at scale. On the same time, we have many other frameworks in the industry around using Python packages and libraries like scikit-learn and TensorFlow and others that may work as a microservice. So the overall architecture should be one that you have sort of a data lake or data sets running on a shared medium, cluster file system, HDFS, managed databases, whatever. And on top of it, you need to have those microservices, and the microservices can comprise of portions of them will be Spark jobs or Spark-based containers, and some other will be other like API functions and model serving functions, where Spark may not be the best tool for the job. So essentially, we want to create a single cluster that have those two types of workloads in a single environment. This is really where things like Kubernetes come into play. So you want to have one cluster where you have a single framework for scheduling different workloads, and Kubernetes is quite generic, unlike things like Hadoop, which is very specific to big data workloads. And it's also pretty secure and has a very vibrant community, which allow you to leverage all those innovations that have been done there for the recent years. Okay. So again, we want to move from Hadoop architecture, which is sort of keeping stagnant and is not really cloud native. What does it mean, cloud native? It means essentially being able to drive workloads through a more agile architecture as microservices. If they fail or need to scale, that is done automatically using containers versus virtual machines or non-isolated workloads on top of Hadoop. So this is what we want to move into an architecture where the data layer is becoming, instead of a file system like HDFS with all of its limitation and very exhaustive of resources with all the replicas, etc., and we want to move into a managed storage or database framework. Managed storage, things like object store in the cloud or managed databases. The next layer of scheduling, we want to move from a single trick pony like Yarn into something very generic that can run any type of workloads and have a vibrant community, as we discussed, which is called Kubernetes. And instead of running middleware, which is very specific to big data workloads, we want to run all the different middlewares, all the different services on the same cluster and not have to manage those frameworks independently. And then we can focus on running our business logic and not focus too much on managing those clusters. So what is Spark over Kubernetes, or how does it work? And in a minute, we're going to see a live demo by Marcelo. And the general idea in Kubernetes is everything is a container. So you essentially, or a pod, which could be a set of containers. So we want to essentially go and launch such container. And in Spark, we may have different types of containers. We may have like workers and executors, and we want to have a driver, which is the thing that launches the job and manages the lifecycle of the job. So the first step would be to talk to some service on the cluster. We're going to see in a minute how it's done, because there are different ways of doing it on Kubernetes. And this service is going to essentially go and spawn the driver and the worker, assign resources like storage mounts, configuration, CPU, GPU resources into those workloads and launch them, and also manage the lifecycle of those jobs while they're running. So for example, if something failed, it will automatically restart the resource. If there aren't enough resources, it will essentially notify us, etc. So this is what the Spark over Kubernetes provide us is a mechanism to launch Spark-based containers and the orchestration associated with them, with pushing the drivers and the workers and potentially other services for shuffling and other on the same cluster, and then manage the lifecycle of the job. Now, with that, there are essentially different ways to skin the cat, as you say. There are three different mechanisms, and Marcelo is going to cover those as well as demonstrate how it works.
Hi, my name is Marcelo Litovsky. I'm a solutions architect with Iwasio. I'm just going to continue on what Yaron was talking about as far as how to run Kubernetes, how to run Spark on Kubernetes. And there are different modes of running Spark on Kubernetes. But they all require, first of all, that you have a Kubernetes cluster up and running, that you have the right permissions, and you have the right components deployed to that platform. So the first way of running a job in Kubernetes with Spark is where your driver runs outside of where the rest of the Spark cluster is running. So your driver will run on a container or a host, but the workers will be deployed to the Spark, to the Kubernetes cluster. There are some advantages or disadvantages of doing all three of them, but it all depends on your architecture and how other applications in your environment are running. In the second case, you are submitting the Spark job, but even the driver runs inside the Kubernetes cluster. So you have everything running inside the cluster. You still have to interact. There's several dependencies as far as being able to interact with your Spark jobs. So in the first two, there is a lot of things that happen outside of the Kubernetes cluster that you need to be aware of, and access that you need to be able to monitor the job to understand what's going on. And the last option is to run it as using the Spark 4K88S operator, which is basically an operator in general in Kubernetes has uh, the the full template of resources that are required to run that type of job that you're requesting. In this case, it's a operator for Spark. So it knows when you deploy your application that it needs to deploy a driver, that it needs to deploy a worker. It knows based on your specifications how many replicas of each of the workers is going to deploy. And then you can let Kubernetes run that cluster and use the Kubernetes tools to be able to monitor how you're running. So, like I mentioned earlier, there's three different modes of operation. When you're working with the driver running outside of the cluster, the main thing is that you have to be aware of that communication between your your workers and your driver. You also need that access to Kubernetes to be able to deploy the resources. So you have to have what is called a Kubernetes config file that determines who you are. It's kind of like a login to the cluster, and it will allow you to connect and establish all the deploy all the resources. Uh, in the first case, like I said, the driver will run on your container or your on another host, but then the workers will be running on the Kubernetes platform. So the first two are very similar. You know, there's a lot of things that are outside of the platform that you have to be aware of, and you have to manage outside of Kubernetes. The last one is a little bit different, where uh, when you deploy a Spark job, um, the account, the service account, and I'll show you that in a demo, that is associated with that job will have the ability to do that full deployment. And once you let that job start, you can interact, like I said, with Kubernetes, with the commands that I'll show you in a couple of minutes, to be able to monitor the job, to understand if errors are happening, how to look at the logs, how to communicate with the Spark cluster, the UI itself. So those are things or components that are built into that Spark operator for Kubernetes. So now I'm going to give you a quick demo of doing things with the Spark operator. Well, let's make sure I share my right screen. All right. So the first thing, like I mentioned, is that you have to have the Spark operator running on Kubernetes. I already have it installed. So if you use Helm, which is the package manager for Kubernetes, you'll see that I have a version of the Spark operator running in my environment. I can look at any applications that have already executed. So I can look at what I already run in this cluster, and I can deploy new jobs. So the way I will do this, I have the YAML that defines how you deploy that job into Kubernetes. So I have actually this is part of a GitHub project that we'll share shortly. So first of all, I have my Python script, and I'm using examples from the Apache Spark project. So this is just a simple PySpark script that does a basic calculation, and I have the YAML that is going to give the instructions to the Kubernetes cluster on how to run that script. And there are a few things that you have to be aware of when you're looking at this YAML and you start building. First of all, the version of the operator that you're working with has to match what you are deploying. So this is the version of the operator that I'm running. Um, then there is the image that you use. In this case, I'm using a Python. I'm going to run a PySpark script. So this image, a Docker image based on uh, PySpark. If you're using Scala, you're going to need to use a different image. This image also has to be built so it has all the dependencies that each of the workers will need to execute. Now you can start like I did using the images that are already provided by the Apache Spark project, but you can build your own based on that image just to make it easier. You can add your own packages to that image. I'm also taking my application. Is the application is not the actual script is not part of the image. I'm going to pick that up from a GitHub project. I can also run it locally. Now, the caveat there is that you have to be aware that when this container executes, um, it's running on Kubernetes. It does not know anything about your local file system. So you have to understand how to mount the required file system in order to be able to access a file that exists elsewhere that is not inside that container. The way this image, this YAML was built, and because I'm running on a single node Kubernetes cluster, I'm able to mount my temp directory inside that container. So anything that I put in that temp directory will be available to Spark as the application runs. I'm also defining the limits of the resources that I'm going to consume. So if you're used to Yarn as a resource manager, there's a lot of complexity to managing Yarn and managing permissions and resource allocation. Kubernetes makes that a little bit easier. So you can, as part of the spec of running your application, you can define how many cores, how much memory. If you need to use GPUs on your process, you can also allocate GPUs to that container. And this is as long as your Kubernetes admin allowed you to request those resources as well. There is some configuration on the Kubernetes side that limits what you can access. So I have a definition of what the driver, I've been calling it workers, but executors, what the driver and the executors, what resources are going to request, the file system that I'm going to mount. And in this case, I'm mounting, and this is a bad practice for production, but I'm mounting a local file system just to do the testing. Um, and then I also specified on the top the script that I'm going to execute, which is going to come from a Git repository. I also have, just to show you, I did another YAML that I alter slightly to pick up the file instead of the Python file from a Git to pick up the file locally from the temp directory. And I'm able to do this because I mounted that file system inside the container. So whatever is in the temp directory in my node is going to be available. I'll be able to execute that application as well. So in order to run this application, I have the YAML. What you have to do is you have to tell Kubernetes to deploy the application. Now I have run the application in advance, so this is going to end very quickly. It's deployed to the cluster. Now it's running on the background, and obviously you need a way of being able to interact with the cluster to know what the job is doing and how is it operating. So the first thing is what I showed you earlier. You can run a get application. So we know that the one that I just executed should be here, or is probably still deploying. Then I can look specifically at that application. Look at the pods that application is running. And you can see that now my driver and my worker, I had one driver and one worker. The worker should be coming online shortly. So those are running. Now, as you start doing development, you'll likely run into some errors. Some things are not going to be available. Some things are going to be missing. So you want to be able to interact with this pod, with this application, and understand what's going on. So you can use the Kubernetes commands. There's a Kubernetes command called it's logs that will let you look at the logs of the driver. So you can see exactly what happened. So if there was an exception or an error, you will see it here. And you can also see the output of the script. I believe that this one is still, the one that I just triggered is still executing. So if your job is executing, you can do a -F. That actually tells the execution log. But I guess by the time I did that, it had finished already. And as you look through the output, you should see the result of that calculation. And it is a lot of output because I'm debugging the application. But I'm missing it because it's only a single line of output. I'm going to do something much easier, which is grep, so we can see. So basically, this is the output of my script. I have the version that I have for the local file system gave me a more interesting output, but I run the one that is on GitHub, so it is different than, it has a different layout of the output. So just to do a recap of how to look at your application, how to troubleshoot, and I'll close the demo with that. Get Spark applications, will give you a list of all the applications that are running. This is the application that that was executed earlier. If you want to look at the pods based on an application name, you can look at the pods with get pods, and I'm just doing a grep for the that application that I'm running. And the last thing, the more importantly, is to be able um, to look at the logs to can see the output. Uh, Now, when you're done and you want to clean up, the last thing to do if you want to keep your cluster clean and not have all those applications laying around, you can actually delete the application. Before, when I did the first command, I didn't apply. We took the YAML and created the application and run the code. I do a delete, and my application will no longer be. That was a typo. My application will no longer exist. So when I do I get Spark applications, that my application no longer exists in the cluster. So this is how you handle running a Spark for Kubernetes job using the YAML and using all the kubectl commands. This requires a good amount of understanding of how Kubernetes works. You have to make sure that your YAML is formatted properly for that version of the Spark operator. You have to make sure that the location of your Python script or your Scala script is available to the containers when they execute. So that means that you also have to make sure that you can mount uh, correctly whatever file system resources you need at runtime. And with that, that was the end of the demo. Let's stop sharing my screen. Let me go to the next slide. I do have a repo with the demo that you could reproduce this on your desktop with Docker for desktop, for Windows, or for Mac. I did this repo last year for our MLOps conference, and it probably needs a little tuning. Before you watch this video, I probably will go in and make the necessary changes so you can execute on your laptop as well.
Okay, thank you, Marcelo, for a great demo. And let's continue and see how potentially we're going to improve the experience through some additional tools. Because as you see, some of the challenges around DevOps still exist. We need to configure YAMLs. It's not so trivial for someone that just wants to launch a job. And we need to configure the resources and security attributes and volume mounts and all of that, and package dependencies. So there are still a bunch of things that we need to address. Also scaling and scheduling of the workloads in a slightly more automated fashion. And also how do we integrate with other frameworks? How do we embed various packages into the image that we want to launch? So we need to build images every time we launch. So there are still a lot of challenges that force us to spend a lot of DevOps resources. And this is where we're trying to improve the experience with some extra functionality that we've added here in Iguazio. So the first idea is, we said, how do you automate DevOps today? And the way to automate DevOps today, the most automated fashion of DevOps today, is the concept of serverless functions. If you go to, for example, Amazon, you have Lambda functions, you write some code, you click, and now you have a function that runs in production and responds to HTTP requests, okay? So no one needs to build containers, no one writes any YAMLs, like Marcelo showed us. You just write code and you deploy it. But the key challenge is that while serverless is very friendly, very nice, there's resource elasticity, you don't use it, you don't pay for it, you automate the entire lifecycle of development and operation, it's still not a good fit for data intensive and machine learning workloads, because there are different attributes to those workloads and serverless functions. So today, if we examine existing serverless technologies today, they have very short lifespan. After 5 minutes, your Lambda crashes, and you may have jobs that run for 30 minutes for training. if you're running scaling, you want to scale your workload. Serverless technology usually do that using an API gateway and a load balancer that throws different requests at different containers. While if you're thinking about Spark and other technologies like Dask or Horvath or other machine learning and data analytics frameworks, they're using other strategies like shuffle and reduce and RDDs in the case of Spark, um, or potentially hyperparameter tuning with some other frameworks. So we need a different approach at scaling. And also, in most cases, it's stateful because we're processing data. So if serverless functions are usually stateless and you attach to resources through some HTTP calls or S3 calls, you want to be able to access data from your function in order to process and analyze it, not necessarily through an HTTP hook. Um, and the last thing is when you're running a job, you're not passing a JSON event as the request, like usually in every serverless function that are RESTful typically. What you want to pass is a set of parameters for your job, and data sets. This is the input data. This is the query I want to run on the data, or this is the input data, and this is the model I want to train with those parameters. So there is a different input. So with that, we understand we cannot just use a serverless technology that was invented for event-driven or real-time workloads like Lambda, or in our case, the open source project called Nucleo, which we maintain. We need a different story. We need to extend the serverless and still maintain the inherent benefits of elastic scaling, not paying for things that we don't use, and automating the DevOps work. But we want to apply it to the problem at stake. So we want to potentially think of it as a serverless Spark or serverless Dask or serverless Horvath. And this is really the idea behind what we call Nucleo ML functions, or in combination with a framework called MLRun, which is automating this work. So we've seen that within Kubernetes, there are things called CRDs or operators. They know how to take code and through a spec, usually described through a YAML file. They take those two things and they run a job and then they finish. Okay, so we understand that there is your code or a service that runs something. There's what we call a runtime, which is this operator, and we could have different runtimes. One's for Spark, and one's for just regular jobs, or one's for Dask if you sort of more in the Python camp, or Horvath for deep learning, and Nucleo for real-time functions, etc. So are different types of resources that embody the code. So we want to create a function that comprises of those two things: the specification and the resources along with the code, and abstract it in a certain way. And then we want to define the contract between those functions and the user. What does the user want to do? He wants to pass data, parameters for the job, potentially secrets and credentials, because if my function is going to access some external database, I may need the password. So, and I don't want to pass the password through clear text, so I need a mechanism for passing credentials into my code. And once the function finished executing, it's going to generate some outputs. It's going to generate results, for example, accuracy of my model. It's going to generate operational data like logs, telemetry data, monitoring CPU usage, etc. And it's going to generate new data sets. Like, I'm running analytics, I have a source data set, and then I have the analyzed data set with the join results or whatever. Same for models. I'm running a training on some data and I generate a model. So what we want to define is such a box, a virtual box where we throw in parameters and data and secrets, and we get back results, logs, and data artifacts through a simple user interface. And we also want to be able to define those functions as a set of a bigger story, a pipeline. So for example, we may have a function that ingests data, and then another function that prepares the data, and a third function that runs training on the prepared data, and a fourth which does validation, etc. So we need a simple way to essentially plug those functions into such a generic architecture. And this is really where we invented the concept called MLRun, which is it's automating these entire things. No YAMLs, you're only focusing on simple code and everything that you see here is fully automated. So, for example, when I have my function, I can write something inside a notebook, and we're going to see a demo in a minute with Marcelo here. So I can take some code and I define a function. The function includes the code, but also includes some definitions of resources like CPUs or jars and things like that. So I can essentially create a Python object that encompasses all the configuration. This is what we call the function, alongside with the code that is, is a pointer to where I'm storing my file, and I can store my file in various locations. And we can use different execution engines. As Marcelo showed us, that there are 3 ways of using the cluster. So each one has some slight advantages and disadvantages. I may want to run Spark locally within my Jupyter notebook, or maybe against a live cluster that is always up and running, not sort of decommissioned when I'm not using it. But on the same time, you want to run exactly the same job against a cluster that is built ad hoc for my job, and I have a way to customize the image and the Spark version that I'm going to use, and all the packages that I want to, or jars I need to use for that job. It provides me a lot more power, and it's only going to be used while I'm launching the job, so it saves resources. On the other end, there is some downside, like it takes some time to spawn this cluster and create that. So if we have very short tasks, we may not want to do that. So you see in this mechanism, I can just run exactly the same code without modifying too much, just few configurations. Can run the same code locally inside my notebook, and the same code with slight configuration change in a cluster in a distributed fashion. And we're going to see that in a demo in a minute. The other point that I mentioned is that we want to compose a workflow from all those different function instances. And the best solution in Kubernetes to run a workflow is something called kubeflow, meaning Kubernetes and workflow, or kubeflow pipelines is a specific project, open source project initiated by Google originally, and other companies. And you could essentially just plug different steps within a pipeline and say, you know what, the first step is getting the data, the second is preparing and training, and so on. So we can use this tool, which is great. It also knows how to record information about artifacts and logs and other things. And we also couple it with another tool called MLRun, developed by Iguazio, and it's open source, that allows me to track everything in a very easy way, as we're going to see in a minute. No YAMLs, no kubectls command, just everything through UI or notebooks, or and we're going to see that in a minute. So introducing serverless into a pipeline allows us a very simple composition of such a workflow, because every step in that pipeline could be a self-managed function with its own lifecycle and versioning and images and definitions that we define only once, we store it, and then we pull it in when we need to use it. Another thing is that we can take a single workflow and combine jobs, as some of them are simple Python jobs. Some of them are, maybe Go code or Java code. Some of them are Spark jobs, etc. Some of it is maybe TensorFlow service. So we can combine all those different things into a single pipeline, unlike solutions like Hadoop, where we're very confined to just a set of microservices for big data. One example of a solution that is deploying this technology in production is a company called Payoneer. That's one of our customers, and there is a public use case around what they've done. They're a unicorn in the payment services, and they wanted to achieve 2 things. They originally had Hadoop clusters, and they want to achieve 2 things. The first thing is move from fraud detection into fraud prevention, which is very critical for their business, because if they can prevent fraud, it impacts their bottom line. They can make more money, they can take more risky proposition. And the second thing they want to solve is cut the time to production. So instead of having very long release cycles, investing huge amount of resources. They want to be able to just update things and launch into production in more sort of a CI/CD fashion, an agile mechanism that's enabled through the microservices architecture. So the first solution that they had based on Hadoop was too slow, very cumbersome. So, for example, a typical ETL workload, you take data from the SQL, you run ETL using Spark, you run some aggregations and some processing on that, and then they use some R server to predict. This entire process from the ETL job to prediction and blocking the customer fraudulent transaction was taking 40 minutes. 40 minutes, that's pretty long time, and it allows you to steal a lot of money if you want to. So that's not an ideal solution. The next is managing Hadoop and Spark in this cluster silo is very resource intensive, as many of you have known, and it takes a lot of time to productize a new application or a new version of that application. So with that, they wanted to move to this architecture, which is entirely serverless, fully automated. So they achieved two things. One is everything is becoming real time, and the second is fully automated DevOps and deployment of software. So they can deploy a lot more versions of the software actually on a weekly basis. Every time they want to change the model, every time they want to change the logic, very easy to do. And in the same time, they manage to get real-time performance with this microservice architecture. So the example is now instead of doing ETL, they're just going to ingest the data through CDC, through a stream, using RabbitMQ. The first stage is using Nucleo function. It's a serverless function. They have native support for RabbitMQ protocol, and they're real time, so they can essentially ingest the data, crunch it immediately, and pass it and write it to a database in a sort of a slightly cleaned up way. The second step is a Spark function, which essentially runs also as a job, periodically process all the data that was ingested and combining real-time data with some batch data. The third step is using the model training functions, which are simple Python functions with scikit-learn in this case. So those functions essentially read the data from the database or the feature store, the data that was generated by Spark or by the real-time ingestion function. They build the models out of that data, and they store the model back into the database or the system. And then you have model inferencing functions that actually listen on the live stream of events, and based on the enriched data that was generated by Spark and the real-time data that was generated through the ingestion function, they make predictions. And if they suspect that the transaction for that specific user is a fraud, they essentially just fire an event immediately into the database and change the user state to blocked. So this entire process takes about 12 seconds from the minute we got the event, and we pass it through some real-time analytics pipeline until we actually block the account. So it's from the first indication of fraud. So likely the user will not be able to steal money because it's like instantly going to block the further transactions that it's going to do on the system. And the other aspect, as I mentioned, is because it's serverless with automated DevOps, and then that means that you can do releases as much as you want. Everything is rolling upgrades without even taking the system down. All the monitoring, logging, telemetry is all built into the solution. You don't need to develop anything to achieve that. So with that, let's move into the second demo of showing more of a serverless architecture for Spark and Kubeflow.
Right, so Yaron gave you an idea of all the other elements that have to exist to be able to incorporate this as part of full ML application. We also talked about the complexity that it adds to do everything in YAML and kubectl, kubectl, And then how we can do it using MLRun, which is a component that allows you to encapsulate all those resources that you need to run your Spark application without having to worry about the YAML, the images, and everything else that goes with that infrastructure. So I took the same code that I run from the command line using the basic um, Kubernetes, Spark operator for Kubernetes. I added some artifacts of MLRun to be able to keep track of what I'm doing. So I'm basically logging in into MLRun, and you will see what this does when I execute it. Um, so when you start wanting to keep track of your experiments, it's good practice to log in artifacts, log in results, so you can keep track of everything that you execute. So in essence, this is the same script, except that I send the output instead of printing to the output to standard output. I'm actually saving it to an artifacts database, and I'll talk to that in a few minutes. Now, as a developer, you're working on Jupyter notebooks, and you want to test the full extent of your application from running it in your notebook to run it at scale in Kubernetes. So when you run on your notebook is a single container, and it has limits of how many CPUs, how much memory you have allocated. You might need GPUs, and you don't have GPUs. So there's some constraints. So how do you go beyond that environment to be able to execute your Spark code, your PySpark code? So MLRun gives you the ability to um, use the MLRun API and facilitate that communication with the Kubernetes cluster. So your script can run seamlessly in the Kubernetes cluster, but without having to exit your notebook. So I have a few definitions that similar to what you saw on the YAML, but now I'm using specifications. I'm using a language that I'm more comfortable with. I'm defining where my script is. I'm defining how much memory, how much CPU I'm going to use, how many replicas of how many executors are going to exist. Um, I'm picking up the dependencies, the jars that I need to be able to run my code. So I'm actually leveraging what I have in the context of my Jupyter notebook to lift all those dependencies. And then instead of having to write the YAML, I use MLRun to define the simple things that I need to be able to execute this. First of all, it is a kind of it's a kind Spark job. So this is going to be a Spark job. It's going to use this image as a base image for the execution. I provided the location of the script, and as you can see, it's going to be local to the image. So I have to know that that it's going to be mounted in the location that I expect it to be mounted at, which if you once you start learning Kubernetes, you see that there's multiple ways of doing that. Now with MLRun, will give you a few tools to do that without having to worry about that complexity. First thing is to be able to mount Iwasio's own file system. So I can mount with a simple command, mount the file system. We also have a function to mount a persistent volume claim. So you can mount a volume from another volume that is outside of Iwasio. So that guarantees that you have access to the file system in the same way that you have access to the file system in your notebook. So the container environment is going to have a very, very similar path to everything that you're running. There's a few things that are specified that I needed to run within our environment. And then I define the limits, the requests, and the number of replicas. The same way I did in the YAML, but like I said, in this case, we're using stuff that a developer will be used to and things that are friendly to a developer. And then I
Yeah,
can
I
run.
think another point, Marcelo, potentially to add is the function definition is reusable across jobs. So I don't have to repeat the definition of this function and its replicas and CPUs. I do it only once and then I execute it multiple times.
Yeah, so this object becomes part, and I'll show this in this capability in a few moments when I show you what's next on this notebook as well. So I define this and I run it. Now the interaction with the execution is within my notebook, but it's running and it's building the Spark cluster on Kubernetes, is running my code, and you will see the same output that we saw when we run it from the using the YAML. So somewhere around here, I'll see that that py result, and I keep missing it. Um, it is a lot of output on these jobs. There you go. So I formatted a little bit different, so it'd be highlighted. Now, the other thing is because I run it within this framework, if you look at the bottom of the job, you have a definition of any input, any outputs, any artifacts that I might have recorded during the execution. I also have a link to look at the history and the execution of this job and any artifacts associated with it. So MLRun provides a UI that gives you access to the execution of that job. You can also here, you can see the logs as well. So there's a UI that you can use to see the logs. There is a version for each execution of your job. So as you're running experiments, if you're recording results, if you're recording information of your execution, then you can look at the different versions of the jobs and the different parameters that you use. So by just wrapping around that PySpark script using the MLRun libraries, you'll be able to keep track of all these experiments. And more importantly is that me as a developer, I'm not constrained to the resources that I have on my notebook. I can leverage the Kubernetes cluster seamlessly without having to worry about Docker containers or YAML that I have to build to be able to execute the job. Now, I run that as an independent job, but usually it's not going to be a single job and that's it. There's going to be a pipeline and a sequence of events that you have to follow to, Spark might be doing the data processing, but you might have a TensorFlow job that is going to do training on the model. So we can take the exact same function as Yaron mentioned earlier. I do not have to redefine how that is going to be executed. I use the Kubeflow DSL to define the pipeline. I take the same function as I define it above, and now I can actually incorporate it into a pipeline. I can run the pipeline from my notebook, and at the end of the run, I'll have an experiment link that will take me to Kubeflow. We have integrated Kubeflow 1 with Iwasio, so you'll see that execution of that Spark step as part of a pipeline, and you'll be able to see as well the logs and of the execution. Now, obviously, this is a single step, and there's more complex pipelines. I'll show you another example of a pipeline that has a lot of, that's the typical processing of machine learning pipeline. Um, we're looking at, getting the data, training the models, providing you a summary of the data as you consume it, as well as part of the pipeline, deploying the process. And if you're getting data or your data prep step was a Spark job, you can run that as part of the same pipeline, mixing steps that are run Spark for Kubernetes jobs with TensorFlow, with other components of your pipeline that are developed by different teams within the application environment. So the key thing is, for me as a developer, is the ability to do all this using something that is very familiar to me, that puts together the full machine learning pipeline, leveraging not only Kubernetes, but we're leveraging Kubernetes, we're leveraging Spark for Kubernetes, we're using Kubeflow to build pipelines, as well as Yaron mentioned earlier, serverless components to be able to do inference in real time. And with that, I'll end my part of the demo.
Thank you, Marcelo. That was a great presentation and a great demo. I think what we've seen through Marcelo is how, on one end, Kubernetes is great, as we mentioned before. It provides you a single cluster that you can run all your different workloads, all the modern workloads side by side with traditional big data applications, Spark, Presto, Hive, all those can run on Kubernetes. The challenge with running Spark on Kubernetes is that there's a lot of manual work associated with that, and a lot of DevOps work, messing with YAMLs and kubectl commands, etc. And what we've seen is throughout this serverless approach that we've introduced with MLRun, you have full automation of essentially launching your job from within the notebooks, together with various configuration. Those functions, by the way, they're also stored in a database. So I can always pull them in later and use them, or I can plug other functions from a database into a new pipeline that I've created. And you have all the logging of your outputs presented directly to you in the Jupyter Notebook. So you don't need to wander around with CLI commands, or recorded in this tool called MLRun that I can just go later and see what was running, what was the Git commit version of the job that was running, what were the results, etc., for everything that happened. And I could launch jobs per UI, and all those things will make my life much easier. So with that, and again, thank you, Marcelo, for the demo. We and everyone that wants to learn more about those technologies, about how to run Kubernetes on Spark, or how to further automate that using serverless technologies, just ping me or Marcelo. My Twitter handle is Yaron Haviv, my full name. You can look me up in LinkedIn or other places. And Marcelo will also is very happy to help people usually in those areas.